Today's focus are on LOL diagrams. Okay, so first we got to talk about, before we even talk about LOL diagrams, we need to talk about energy. And LOL diagrams are a form to visualize where the energy is actually going and where it's coming from in a chemistry type of problem, okay? It's really important to understand two words though. One is the system and one is the surroundings. The system is the part of the universe that you are personally studying. So what you care about. So if I care about what is happening to this cup of ice, the cup of ice is the system. Everything outside of that cup of ice, my hand, the air, that is considered the surroundings. Okay, so your system is what you are studying. The surroundings is everything else. Now, when I say an LOL diagram, if you look at the bottom, this is an example of it. So we've got an L, an O, and an L. Okay, this is where your energy is initially, this is where it is final, and this is what is happening, okay, with the energy. Is it going into the system or is it leaving the system? And from this, you can identify whether it's an exo or an endothermic process, okay? So energy is the capacity to change and it is always conserved. What does conserved mean? Conserved means that it is neither created nor destroyed. So what you start with is what you end with. We're going to talk about the three types of energies that is found in chemistry. First off is phase energy, and that is energy due to the arrangement of how they are arranged of our particles. Now, what does that mean to you? What it's really talking about here is what state of matter it's in. We are going to abbreviate phase energy as E, so energy of the pH, which is phase. Okay, thermal energy. Thermal energy is how fast things are moving. Okay, so thermal energy, how we measure it is we measure it as temperature. Okay, so the temperature change. So if we have an increase in temperature or a decrease in temperature, we are changing our thermal energy. We are symbolizing that as ETH. Okay, and how do you change that? You make the particles move faster or slower. And then we've got chemical energy, which is the energy that is stored due to chemical bonds. So how things are connected. We abbreviate that as ECH, okay, for chemical energy. And how do you change that? You form a new substance. So as of right now, like if I had A connected to B, and then I added C, and then now A is connected to C, and then B is by itself, this would be a change of A's chemical energy. Actually, all of their chemical energy would change. Now, these LOL diagrams that we are going to be introduced to today, we will not be really dealing with chemical energy because we are going to be dealing with the same substance. It's just changing what it looks like. It's changing phases, it's changing temperature, things like that. But the chemical makeup of it will always be the same. So we would always be starting with A to B, going to A to B, just maybe looking different. Okay, so we're going to first have to introduce you to the phase energy bars for each phase. Okay, so here are our energy bars, and what I want you to know is that solids, liquids, and gases, the only thing different between them are your phase energy. Solids phase has the lowest amount of energy, so we are going to give it 1 bar. So how I give it a bar is I just boop, boop, boop. And you always have to give solids 1 bar, always, okay? This is the only type of energy where I'm very, very set on how you do it. You have to give it 1 bar. Liquids, you have to give 2 bars. Why 2 bars? Because liquids have more phase energy than solids do. And then gases have so much energy, you have to give it the full 4 bars. Okay? There is no 3-bar phase energy, just to let you know. Okay? So you will never see phase energy having 3 bars. So solids will be 1 bar, liquids will be 2 bars, gases will be 4 bars. Okay, we are going to first off understand that if you have a heating curve or any type of curve like this, when you are changing your phases, when you are changing your temperature, you are only changing one of these at any given time, okay? ETH is when you're changing your temperature. EPH is when you are changing your phase. So I'm going to say purple is phase and blue is thermal. You don't need to, I'm just trying to do this to do the notes. Okay, so this guy right here is changing my thermal energy. Only if I'm at those areas am I changing my thermal energy. only if I'm in these little sections am I changing my phase. If I'm anywhere before or after these, I'm only changing what part of the graph I'm on, okay? So we are heating water. So where am I at if I'm heating water? First off, I know that it's a liquid because it's water, okay? And all I am doing is heating it. So I am at the liquid state and I am going from somewhere, let's say here, to somewhere here. I am only changing my ETH, okay? It is still water the entire time. So what I do is to fill out my LOL, you always have to have some sort of chemical energy. It's just not going to change. I always fill out 1 bar for chemical energy. Okay, it shows that it has it. It's minimal, okay, but it's got it. Okay, you can't have no chemical energy, so I'm going to keep it 1 bar, but it's going to stay the same. For all of your LOL diagrams, this will stay the same for this unit. Okay, the next thing I always try to think about is what am I changing? I am only changing my temperature. Okay, so what am I keeping the same is my phase. I am a liquid the entire time because I am water. And what is liquid? How many does it have as far as bars? It has 2 bars. So I'm going to put down 2 bars for my phases. This is my initial, this is my final. I have not changed my state of matter at all, so I have 2 bars the entire time. Why is it 2 bars? Because it is a liquid the entire time. If it was a solid the entire time, it would be 1 bar, both sides. Okay, but I am heating it up. So whatever thermal energy, I just usually start at 1 if I'm going to go up. Whatever happens to your energy or your ETH, it just has to go up. I don't care how much it goes up. I'm just going to go to 2 bars this time, as long as it goes up. All right, so now we have our bars all done. The only thing you can change is one of your E's at any LOL diagram. So in this one, I change my ETH. I cannot change in my same LOL diagram an ETH and an EPH. Okay, and ECH will always stay the same. The next thing you need to do is figure out this energy flow. So my system originally had 4 bars. And remember, you could have had any amount of bars for your ETH as long as it went up. So mine had 4 bars. My final one had 5 bars because it's 1, 2, 3, 4, 5, right? So I went from 4 to 5 bars. So what does that mean? I had to add energy into the system. So what you need to do is you need to draw an arrow of where the energy is going. In this case, it's going into the system. And then you need to write how many boxes you added. So I went up 1 bar, so I'm going to add 1 bar. If I went up 2 bars, I would have had shown 2 bars going into the system, but I only did 1. So this is what my final LOL diagram would look like. I also see that it's going into the system. Into the system means that this would be an endothermic process because the arrow is going in. Okay, let's try a freezing water. So freezing water, if I think about my diagram, I am going through a phase change. I am freezing. So what do I notice about my ECH? Well, once again, ECH is the easiest. I just do my ECHs right away, always with 1 bar. Then what I'm going to do is what am I changing? I am only changing my phase during that time. So I am freezing, which means I'm going from a liquid to a solid. So because I changed my phases, I know in this LOL diagram, I cannot change my ETH. Okay, but I'm going to worry about my phases right now. Liquid has 2 bars by definition, and solids have 1 bar. Okay, and so because I just changed my EPH, what do I have to do to my ETH? I have to keep it the same, which makes sense because this diagram, this heating curve, I'm not changing my temperature at all when I'm freezing water. Okay, so what I'm going to do is I'm going to say, oh, it's got 1 bar and it stayed at 1 bar because its temperature did not change. So let's figure out our energy flow. We go from 4 bars to 3 bars, which means energy had to get out of the system. And how many? Well, 4 to 3, I lost 1 bar. Okay, so that would be an exothermic process. How do I know it's exothermic? Because it is exiting. That's how I remember exothermic. Exit sign, exiting. All right, so draw the LOL diagram for ice heating up to room temperature at 25 degrees Celsius. So this is a little bit different, okay? So I had ice. Ice is what? Oh, ice is a solid. So I know I was at a solid, okay? And then what's going to happen? It's going to melt first, and then it's going to get up to the 25 degrees. Okay, you have to think through the processes. Okay, if we are at ice in order to get up to 25 degrees, you go through 0 degrees. Why? Because ice is at 0. So in order to get there, you are always going to have flat lines at 0 and 100 degrees for water. I don't get up to 100, so I'm not going to use this flat line, but I am going to use this flat line because I first need to melt it. So all the energy initially is going to go towards the melting phase. So this is going to be my melting LOL chart. Then when I get up to this part, this is going to be my temperature change or my heating change. So notice I have two separate diagrams for two LOLs. Every time you change on this heating curve, you are going to need to change make a new LOL. So if I had it like this, let's just say, I would have, pretend that stops there. I would have 1, 2, 3, 4 LOLs. Okay. All right, so let's deal with melting. So once again, the easiest part is let's just do all of our ECHs first. You can do it on all of the chart, the first thing. Why? Because it's never going to change. We are dealing with water the entire time, so we do not have to worry about changing ECH. Okay, so the first part is I am melting. So what am I changing when I'm melting? Well, I'm right here. I know I'm not changing my temperature. Okay, so I'm going to give my I'm going to melt. I guess I'll go with my melting part first. I am going from a solid to a liquid, which means I go from 1 bar to 2 bars. Okay, now because I changed my EPH, I know I cannot change anything, any other E's. So I'm going to say ETH stays the same at 1 bar. Okay, this process goes from 3 to 4 bars, so I had to add energy by 1 bar into here. Okay, now what I want you to look at is right here on this graph, right here. That represents this part of the LOL and this starting part of the LOL. They are the same. So whatever you have up here, because it is continuing the process for the next LOL, it has to be identical for the next one on the lower left, for the next part. So if I had 1, 2, 1, I'm going to have 1 bar, 2 bars, and then another 1 bar. Okay. Now I need to figure out what I am changing when I'm heating. I am not changing my phase because I'm heating it. Okay, that is only thermal. So I'm going to change, I'm not changing my phase, that will stay to 2. All I am doing is heating up its temperature. So I need to go up in temperature because it's going up in temperature to 25 degrees. So I'm going to add another bar. So I go from this case from 4 to 5 bars, which means I am adding 1 bar to my system. Now, if you look at this, what I really want you to understand is also to kind of like double check, the arrow is always going into the system. Okay, for this particular one. That first off makes it an endothermic process, but at the same time, it will always be an endothermic process for this system. Okay, if the first arrow, for example, was leaving, then the second LOL chart for that same system would also have to be leaving. The arrows always found if you're talking about the same system of the same problem, they will always go in the same direction. Okay, so if it changes up, then you did something wrong somewhere. All right, hopefully you have a basic understanding of an LOL diagram and have a great day.